بسم الله الرحمن الرحیم و الصلاة و السلام علی محمد و آله الطاهرین. السلام علیکم و رحمت الله. مستر ابتسام، مستر یاسر سلام، مستر سعدد، مستر احمد فواز، مستر عامر سعید، مستر بیادر، مستر دعا، مستر حنا، مستر انتصار، مستر لبنان، مستر محمد رشید، مستر صفا، مستر یاسر سلام، مستر زینب، مستر الله Ali Abdul Karim, maybe. Salam, salam. Another lecture about communication in Arduino. Not only in Arduino, but in all microprocessors. For example, Arduino communication, we see about serial protocols supported in communication. Salam, Mr. Amr Said. Salam. Salam, Mr. Intisar. Salam, Mrs. Safa. Salam, Mrs. Hannah. Serial communications, we see RS-232, SPI, and I2C. We said this is UART, Universal Asynchronous Receiver Transmitter. SPI is Serial Peripheral Interface. And Salam, Mrs. Safa. Salam, Mrs. Naim. And I2C is inter-IC connection or communication. Salam. That's right. First of all, we can categorize the communication between parallel and serial communication. Salam, Mrs. Dua. Parallel and serial communication. In this slide, only in this slide, we see about parallel communication. Okay. The simplest of these two, parallel and serial, is parallel. Okay. Parallel communication can be in one-way approach and two-way approach. Okay. Here we see one-way approach, and here we see two-way approach. Here we see this is a data bus from, for example, master side, microcontroller side, to a slave side, to peripheral side. Okay. This direction is from master to a slave. But a parallel, for example, 8 bits or etc. And these two pins, for example, are Salam, Muhammad, Muhammad, Salam, Alam, Salam. These two pins are for control, for handshaking. This is okay. I got project of almost all of you, except 4 of you, okay? But almost all of you is, yes. No, Mr. Safa, maybe, 1 minute, Mrs. Safa. No. Here. Safa Abdul Jalil Al-Musavi. 5 files, okay? 6 files. I don't got them. That's right. Don't worry, I collect them. Salam, Mr. Allah Ali. Maybe Allah Ali Abdul Karim. Salam, Mr. Ali Abdul Abbas. That's right. Allah Kamal Ali. Hasan. Okay. We said this is one-way parallel communication. Okay. These two pins for control, for handshaking, for control bus. Okay. For example, latch for latching the data inside this peripheral, and chip select for selecting this peripheral. Okay. Okay, Mrs. Safa. And this is two-way. The data line V microcontroller can read data in parallel format from peripheral, or send a data to the peripheral. Okay, as parallel. Inshallah. I speak them. I speak them. I speak Dr. Rahmani. I speak Dr. Abnusi. Maybe. Okay. Inshallah, the problem be solved. Mr. Yasser. Maybe Mr. Yasser. Some of you has a 1 day delay, okay? Some of you. I don't got Mr. Al-Khal. Here is Al-Khal. Here. Mr. Al-Khal, okay? Al-Khal. And Mrs. Safa. And Mr. Allah and Moonshine. Moonshine is Dua Ali Abed. Dua Ali Abed. Okay? But all other I got them. Mr. Yasser Salam. Maybe. Mr. Yasser Salam. Mr. Yasser Ali is here. Mr. Yasser Salam. Okay, this is the time of class, the class. I search it. 1 minute. Salam. Oh. I don't know. Okay, all of you. Okay, all of you. Al-Khal huwa hisabi. Oh, okay. Mr. Yasser Salam. Al-Khal hisabak. That's right. Don't ask me again. Okay. After the class, for example, at night, Mr. Yasser said that Zainab. Ms. Ibtisam said, why you say Zainab? You must say Abi Zainab or Abu Zainab. Ms. Ibtisam. That's right. Here we read. This was the Telegram communication. Okay, in one way and in two way. The Sepsam is typing. This is resource expensive in pins, in real estate. خب أنت تقول أبا زينب لا أم زينب. Ibtisam Saad is a girl, a woman. Ibtisam is a boy. Ibtisam. Salam, Mr. Ala Abdul Karim. Ibtisam. My son name is Mesbah. Okay, in Iran, someone he's a girl. Okay, ابتسام. Maybe. Salam Mr. Mace. Salam. That's right. Zainab. Okay, Zainab. That's right. Here we say, Zainab is typing, this is resource expensive in terms of hardware, but easy to implement. Okay, only this slide is about parallel communication, but other slide of this lecture are about serial communication. Okay, this the serial communication. Many fewer lines are required to transmit data. That's right. This is requires fewer pins but adds complexity. Fewer lines and a trade-off between complexity and the line of the database. That's right. For example, we want to transport, for example, D6 in hexadecimal, D6 by this clock. Okay, D is 1100110 in binary. Here we see in the rising edge of the clock, we see 110 10110, etc. This is a serial communication over a single line, a single data line. That's right, from master to a slave, and these are the control bus, clock, chip select, etc. Okay, in serial communication we have two approaches, synchronous approach and asynchronous approach. Okay, in synchronous communications requires a clock for synchronization. Okay, whoever controls the clock controls communication speed. For example, who controls the clock? The master, the microcontroller. Okay, controls the clock. Thus he controls the speed of serial communication. That's right. For example, the baud rate. For example, 1 megabit per second, 10 megabit per second, etc. The speed of serial transmission in sync mode is defined by the clock speed. That's right. But asynchronous transmission has no clock. But a speed must be agreed upon beforehand. That means we had in Arduino, we had a serial begin. Okay, we say, for example, serial dot begin in parentheses, for example, 9600. USART was a universal synchronous asynchronous receiver transmitter. But UART in AVR we have UART. UART means universal asynchronous receiver transmitter. That's right, only asynchronous. We don't have a clock in UART of Arduino. That's right. Okay, again we see with a figure serial communication, asynchronous versus synchronous. Excuse me. Asynchronous from device A to device B, we only have for example 2 lines for a full duplex communication. For example, from TX to RX, transmitter to receiver, and from TX of device B to RX of device A. That's right, only 2 pins. But in synchronous we have another pin named clock. Okay, for example, at least 3 lines or 3 wires. One of them is clock, another from device A to device B, and another from device B to device A. That's right. This is a difference between synchronous and asynchronous. Is one better than the other, or one is better? I zoom in. It depends on your application. In your application, we say maybe which is better. Async is good if there are only 2 devices, for example, peer-to-peer. Okay, and they are both pre-configured to agree on the speed baud rate. Okay, this is good for asynchronous. Like your Arduino sketches in communication between or Arduino board and or sensor, UART supporting sensor, we can use asynchronous communication. Okay, and both side of them maybe must agree on a single baud rate. Okay, synchronous is generally better for faster speeds. Why? Because you don't need an accurate clock, just the ability to watch to the clock wire. For example, by rising edge of a clock or by falling edge of a clock, we can transfer a bit of data. That's right. And in almost each sense, we can maybe increase the speed of our data. That's right, or transfer. Asynchronous in microcontrollers. This UART version. Okay, this UART. Commonly used for one-to-one communication. There are many variants. The simplest uses just 2 lines. In a standard, we can use 6 pins. Okay, for UART. Then we can use 4 pins. Then we can use only 2 pins. Okay, maybe in almost all of our situations, 2 pins is okay. TX and RX. That's right. Transmission process or baud rate, for example, 9600 baud, and the duration of one time slice is 1 over the baud rate. For example, 1/10 of millisecond. That's right. Here, about. Transmit idles high when no communication between 2 sides. It goes low for 1 bit. That means a start bit. Okay, it sends out data. LSPs first, maybe 7 or 8 bits. Correctly, from 5 bits to 9 bits. Okay, for data. In a standard UART. There may be a parity bit, maybe or may not. Okay, when we have the parity may be even or odd. Okay, what's the reason? The parity is for error detection. We said about parity previously. You know parity check. Okay, parity even, parity odd, etc. Each one that don't know what's parity. All of you know? Maybe. There may be a stop bit. Okay, 1 stop bit or 2 stop bit. Here we see a packet of data in UART. Okay, here the line is either is at 1. Okay, logic 1. Or either. A zero shows a start bit. Okay, a 0, a duration of 1 bit, 0. Then from here to here we have data packet, data from LSP to MSP. Okay, by our configuration, for example, 5 bits, 6 bits, 7 bit, or 8 bit or 9 bit. Okay, for example, here we see 1, 2, 3, 4, 5, 6, 7, 8 bits of or byte. Then we see here a parity bit. That's right, a parity. What about parity? For example, here we have this is in even or odd parity. مثلا انتصار or all of you. These 8 bits are the data byte. Okay, the data. This is LSP. That means 8 1. Okay, 1 0 0 0 0 0 0 1 8 1 in hex. And this is parity. Here we have even parity or odd parity. Answer me, one of you. مثل انتصار. أحسنت. Add, no add, odd. مثل يا عبد العباس, odd. Okay, but the answer of مثل انتصار is okay. Even here, even. Okay, what's even and odd? For parity, we count the numbers of ones in the packet. Okay, and all of the ones plus by parity must be even. Okay, for example, here how many ones we have in our data? 1 and 1. We have 2 ones. Okay, here in binary 1 0 0 0 0 0 0 1. Okay, here we have 2 ones. Okay, ones or even. Thus P is or must be 0. Okay, the sum of ones in the packet and the parity, all of them must be even in even configuration. Okay, for example, if we had 5 ones in our data, 5 ones, for example 1 0 0 1 1 1 1. Okay, 0, 5 ones. This is an odd number. Then P must be 1. All of them is 6 and is even. That's right. And after the parity, we see we have 1 or 2 bits as a stop bit. 1 or 2 as a configuration. Okay, 1 or 2 bits. Here is 2 bits of 1 logic as 2 stop bits. After this 2 bit, maybe the clock is as idle as 1, or after some times it goes to 0 for another packet. That's right. Another notation, the voltage levels. For example, in Arduino board, we have TTL voltages, okay, for 0 and 1. For example, here we see in the processor side 0 volt for logic 0 and 5 volt or 3.3 volt as logic 1. Okay, but the line side, the other side, the channel, okay, is plus 12 for logic 0 and minus 12 for logic 1. Okay, and this band from 3 volts to 12 volts for logic 0 and from minus 12 to minus 3 volts for logic 1. As here we see, for example, the previous example 0 1 0 0 0 0 0 1. Here we see 1 is 0, 0 is 1, 1 is 0, etc. 0 logic 0 plus 12 for logic 0. That's right. But the voltage of levels of voltage, not 5 volts. Okay, minus 12 to minus I zoom in, from minus 12 to minus 3 volts for 1 and from 3 volts to 12 for 0, and etc. That means a good noise immunity, a good noise immunity or immunity, that's right, for industrial camps, etc., for long distances, serial communications, etc. And a gap of 6 volts here from 3 volts to minus 3 volts, okay, is a good standard protocol for serial communication. Here we see inside of protocol controller from TTL voltage to channel voltage. For example, IC max 232, max 232, max 232. That's right. IC inside. Here what's this box? Which of you knows? What is this item? And this item, U1 and U2. PSA8802. Each of you don't know. This is optocoupler, okay? Optocoupler for isolation. That's right, but inside of IC, not knowing. Is the physical connection, physical connector, a 9 pins connector for UART. Okay, we see here is a signal ground. 2 pins ring indicator and data carrier detect isn't used. Okay, these 6 pins. Data set ready, request to send, clear to send, transmit data pins may be used. Okay, I zoomed it out. Here, handshaking in UART. Some RS232 connections using handshaking lines between DCE and DTE. This two names is in a standard of IBM, okay, IBM Corporation, and don't use know them, okay. DCE or data communication equipment is for master, DCE is for master, and DTE data terminal client, okay, equipment for a slave. For example, in communication, your Arduino board is DCE and your sensor is DTE. That's right. For 6 pins standard, for 6 pin standard, these 4 pins RTS, CTS, DTR, and DSR. For example, RTS is ready to send, CTS clear to send, DTR data terminal ready, DSR data set ready, not read. For example, one of them ready to send by the DTE, sent by the DTE to signal the DCE is ready to send. Okay, In practice, don't worry, in practice, if these handshaking lines are used, it can be difficult to set up the serial communication, but it's quite robust once working. But we don't use this 6 pins standard. We only use the 2 pins standard, okay? TX and RX, transmit data and receive data. Here, another protocol, the second protocol, SPI, Serial Peripheral Interface, okay? I zoomed it out. Serial Peripheral Interface, introduced first by Motorola. UART introduced first by IBM Corporation. Here, master supporting SPI and a slave supporting SPI. These 4 pins, serial clock, master out, slave in, master in, slave out, and slave select. Serial clock is only from master to slave, okay, from master to slave. Clock generation is here, not here, from master to slave. MOSI, master output, slave input, from master to slave, master output, okay, from master to slave. MISO, master input, slave output, from slave to master, that's right. Slave select, who selects a slave? Master selects it, okay. Slave select from master to a slave, that's right. This is for peer-to-peer, only a master and a single slave. But here, for more than a single slave, some slaves, we see, for example, serial clock, MOSI, MISO, SS1, SS2, SS3, etc. This SS for a slave select of this slave, SS2 for a slave select of the second slave, and so on, okay. Others shared, serial clock is shared between all of them. MOSI and MISO shared between all of them. But select as your project, 2 7-segment, double 7-segment project, okay. Chip select is separated, that's right. Okay, 2 types of devices, master and slave. We will consider only one master. In Arduino, we have only one slave supporting, okay. But you can use, for example, if needed, for example, PA.0, PA.1, PA.2, etc. for some slave selects, okay. But in it, we have only one slave select for one slave. That's right. slave select is active low. That means each slave gets its own slave select when active is low. Pulling line low selects a slave. That's right. SPI and the clock. Pull a slave select line low to select device. That's it, as chip select here. A slave select. This is as chip select for a slave. Okay. First bit of data gets put on MISO and MOSI. MISO, MOSI from master, MISO from a slave. That's right. Go about, for example, in full duplex. So a byte goes both ways, from master or from a slave, from master to a slave, or from a slave to master. Data gets shifted out, typically 8 bits, but not necessarily. Maybe 7 bits, maybe 9 bits. Here we see a slave select is in low situation. Okay, a slave is selected. Serial clock. Excuse me. Here is clock 1, 2, 3 to 8, and these are the data on these data lines from MISO or from MOSI. Bit 1, bit 2, bit 3 to bit 8. Here the data gets out, get put on bus on falling edge of data. Data is on bus on falling edge, and the data gets read on the rising edge of the clock. Okay, for example, master puts the data on the line on MOSI at falling edge, and a slave gets the data, gets the bit on rising edge. Okay, here we see, for example, after a slave select here, the master puts the data over the line, the first bit, and in rising edge, the slave gets the data. In falling edge, the master puts the data. In rising edge, the slave gets the data, etc. That's right. Another one. These are the theory of the problem. Okay, in Arduino, in code programming is very simple. Don't worry. This is the theory of the problem. That's it. SPI and the clock. Clock can be set many ways as determined by clock polarity and phase. Certainly in 4 ways. Okay. For example, in AVR, in Code Wizard, in Code Vision, okay, we have some fuse bits for this SPI. 2 fuse bits. Each of them is C pole, means clock polarity, and the next is C phase, CPHA, for clock phase. Okay, we see here in this slide. For example, we can see C pole is 0 or C pole is 1. CPHA or clock phase maybe 0 or maybe 1. Here maybe phase 0, maybe 1. But here C pole is 0. By default is 0, then high. Okay. C pole is 1. By default is 1, then is 0. That's right. The first one, C pole clock polarity is 0. Base value of the clock is 0. Okay. In normal it's 0. This case, CPHA clock phase is 0. Data read on rising edge and puts on falling edge. On falling edge of serial clock is as the same of the previous slide. On falling edge, we put the data, the bit of data, over the line. In rising edge, we get the bit of data from the line. That's right. But CPHA or clock phase is 1. Is vice versa. Is al-makus. Okay. And data read on falling edge and put on rising edge. Okay. Inverse of the previous slide. This is the inverse of the above. For example, when C pole is 1, that base value of clock is 1. CPHA 0 is as CPHA 1 here. Okay, data read on falling, put on rising. CPHA 1 is as CPHA 0 here. Okay, data read on rising, data put on falling. For example, 4 approaches. Okay, but don't worry, we use only a single one. C pole is 0 and CPHA is 0. The first one. Okay, polarity and phase, both of them are 0. It's simple. As the previous slide. Here, C pole is 0 and CPHA is 0. Clock data bit is put on the falling edge of the clock and is get on rising edge of the clock. Is get from the bus or rising edge of the clock. Okay. Here you see R4. But what this for situation, because of some variant versions of sensors, for example, okay. But don't worry, we only can use the first one. CPOL is 0, CPHA is 0. What do you say, Mr. Abdul Abbas? Different this one, no signal. I don't know what Marcus. I don't know what you say, Mr. Abdul Abbas. You got what I say? What I said? All of these four are the same, okay? Are the same, but by half of a clock. Here you see, for example, this time, for example, rising edge of this CPOL is 1, okay? Here, and this is if half of the clock shifted, okay? Shifted here. On this difference, and there's another difference. All of this 4 is the same. Okay, Mr. Abdul Abbas? That's right. The third one, we said about UART, then we said about SPI, and here I2C, inter-IC communication, okay, or TWI. What was TWI? All of you, what was TWI? Another name of I2C. I2C or TWI. What's TWI? TWI is two-wire interface. I2C is inter-IC communication. IIC, inter-IC communication. Okay. TWI is two-wire interface. Are the same. TWI or I2C. We need only two-wire for interfacing between some many ICs. Okay. As here. This is VDD, okay? This is the power, no line. These two pins, SDA and SCL, serial data, serial clock, is shared between some ICs, okay? In S standard I2C, shared between 128, okay? ICs. But in AVR, max have 16 ICs, okay? One master, al-baqi, others a slave, okay? One master each time, all of them as master in I2C line. Here, as with SPI, a master-slave system. As SPI, we have master, microcontroller is master, other sensors or actuators act as a slave, okay? Also called a two-wire bus or two-wire interface, TWI. It has only clock and data, SCK, serial clock, and SDA, serial data. With pull-up resistors, here RP, pull-up resistors. When each of master or slaves don't work with this line, this bus, both of SCL and SDA are at high level, okay, but pull-up resistors in idle mode. That's right. Lines can be pulled low by any devices. Okay, can be pulled low. That means a start of a session. Okay, a start of a communication, and are high when all devices release them. That means idle mode. There are no slave select lines. Okay, no MISO, MOSI, slave select, etc. Instead, the devices have addresses that are sent as part of the transmission protocol, as part of block, okay, data block. For example, as TCP/IP, you know that in TCP/IP we have data, we have source address, we have destination address. Okay, here in I2C we have destination address, the slave address. That's right. That is put by master address. For example, in a common line of I2C, each of the slaves have their unique address, okay, their unique slave address. And when a packet is shared over the bus, over the common bus, each slave that its slave address is the same as the packet address is acknowledged to the master, okay, and a session is starting. That's right. Some speeds, for example, 4 max speeds, 100 kilobit per second in a standard, 400 kilobit per second in fast mode, for example, 1 megabit per second for fast plus, and for higher speed, etc., etc. I2C is a live protocol, okay, and they are improving it. Another slide. I2C write a single byte. For example, mode of writing. That's right. Here for write cycle and here for read cycle. In 7 steps, okay. For example, first, idle mode. All allow SDA and SCL start high. This is up, okay, and in voltage 1. This is idle mode. 2, master SDA low to signal transmission. One A is for master. SDA go to low for indicating a start of a transmission. That's right. Then 3, master sends out SDA10 and 7 bits of address. 7 bits of address for slave address, okay, slave addressing. Then followed by 0 for write, and followed by 1 for read, okay. Here, first of all, SDA go to low, then 7 bits of address, then here you see here SDA and SCL. Here we see data bits, okay, data bits. Here read write bar, a bit of 1 for read or 0 for write. That's right. I is 1, okay. مثال ابدال بس. Here is for read. Here is for read. For write, it must be 0. 0 for write. Here is for read. Here is read. Then slave. Pull SDA low to signify acknowledge. Okay. After master, a slave acknowledge the master that I got the address, okay, and compared it with my address, and acknowledged to you that I answered to you, I'm okay for transferring, okay, for getting data. We are in write mode from master to a slave. An acknowledge from master is issued to from a slave to master. Then master sends out 8 bits of data on serial data. That's right. After getting an acknowledge from a slave, we as master send 8 bit of data from MSP to LSP over the SDA. That's right. Then a slave acknowledge to us. Acknowledge that means I got the byte of data. Okay. Then the session is over. The session is cut. Okay. All allow SDA to go high when STL is high. That means idle mode. All of them is high. And for read is the same, but after the address we have read, not write bar. 0 for write and 1 for read, as here. Uh, from here, uh, um, number three, master address, putting address over SDA. That means read on SDA. Okay. Then a slave. We are reading from a slave. Master says, I got their acknowledgement inside. It's very this slide, this animation, okay, this notation, this for example, the red color, master to a red color from master to slave, the blue color here, blue, a slave signals from a slave to master. Okay, here for writing mode, master transmitter writing to a slave receiver, and here for reading mode, okay, master receiver reading from a slave transmitter. Okay, write, read, red from master, blue from a slave. It's very good notation. Okay, here first of all, S means a start from master, red color. Here you see A acknowledge, A bar not acknowledge, S start, P stop, R read, W bar write. Class, I put this file over the LMS. Okay. Or maybe this time I'll put our Telegram. You need it just now or after the class? In Telegram. Asani, after the class? What means what do you say, Miss Name? Telegram, in Telegram. Okay. Please wait. Please wait. Groups, embedded sys here, I put it over Telegram. Is coming. Don't hurry up. Half of the file. And transmission is completed. Okay, serial.pdf. That's it. Here. Okay. Mesela Abdel okay. Here we said start from master for write, then a slave address, a 7 bits, a slave address. Okay. Then write bar. Write bar means zero from master. Okay. Me as a master, as microcontroller, want to write to you as a slave. Okay, by signaling the write W bar 0. A from a slave in blue color. Okay, acknowledge from a slave. I'm ready. Me as a slave, I'm ready to get the data. Okay, who is me? Who that its unique address is the same as this this slave address. Okay, then in red color, a data is sent by the master. For example, maybe here we have a stop or another one, acknowledge from a slave, then another data, then acknowledge, then another data, then acknowledge, then another data, then acknowledge. Then from the each time from the master side, a P, that means a stop. Okay. For example, 8 bytes, 5 bytes, 2 bytes, etc. Here you can transfer multiple bytes in a row. Okay, a single byte or multiple bytes. That's right. Here, this timing for reading from a slave side. Each of them, for writing and for reading, the master is starting. The master is starting, not a slave. Okay. Here you see red color. As master starts. Okay. Master puts the slave address over the bus. Okay, over the SDA. Then R means 1, a bit of 1 over the bus. A slave acknowledged to master. Okay, I'm ready to put data over the bus. Me as a slave. Okay. Then a slave puts the data over the bus. Blue. A slave put the data. Master acknowledge. Okay, master is acknowledging. Red color. Another data. Another acknowledge another data. Acknowledge another data. Acknowledge another data. Then acknowledge bar. Acknowledge bar, and then a stop. That's right. And here, at view here, SDA and SCL is the high, that means idle mode. Okay. SDA goes low, that means start. S here, S. Okay. Start signal. Then SCL is clocking by master. Okay, by the master. 0 1 0 1 0 1 0 1 0 1, etc. Then this is the address. I zoom in it. This is the address. B6 to B0. That means 8 bits of address, 7 bits of address. 7 bits of address. Okay, 7 bits of address. That means 2 powered by 7 is 128. Okay, addresses. That's right. 7 bits address B6 to B0. 2 powered by 7, 128 addresses in a standard I2C, not in AVR. Okay, in a standard I2C, in a standard I2C or DWI. Okay, but in AVR only 16 addresses. Then after it, read or write, okay, then acknowledge from the slave side, and then data D7 MSB to D0 LSB. Okay, here for both for address and data, B6 to B0, MSB to LSB. For data, D7 to D0, from MSB to LSB, then acknowledge from the slave side. Okay, and after it stop. Stop means SCL and STA, both of them are in one mode. Okay, in high mode. This is idle mode. This is end of transmission. That's right. Two small hints. Okay, at the end of transfer, a slave can hold SCL line low to slow transfer down, to slow down the transfer. Okay, for example, for some wait, that called clock stretching. Okay, be patient. Okay, I as me as a slave go to master, please be patient, I'm so slow. Okay, another one, any device is over this share I2C bus. Okay, any device can malfunctions, any device that malfunctions can disable the bus. Okay, for example, one of the sensors, one of the peripherals maybe is working wrong. Okay, that can malfunction and can disable the bus. For example, go the CL to the ground. SCL is 0 all of the time, and you must troubleshoot the bus. That's right. Another one, wireless protocols, wireless serial communication protocols. Here, for example, order increasing complexity, power dissipation, and consume bandwidth. Okay, for example, simplicity, bandwidth is lower than 200 kilobit per second. Okay, and lower complexity and lower power dissipation. Here Zigbee is very used in IoT situations. Okay, Internet of Things. Zigbee, for example, 250 kilobit per second, more than this item, more power consumption and more bandwidth. Bluetooth, some Bluetooth standards. Okay, Bluetooth may be from 1 megabit per second to 24 megabit per second or more. Wi-Fi, Wi-Fi A, Wi-Fi B, Wi-Fi G, Wi-Fi N. For example, 11 megabit per second, 54 megabit per second, 150 megabit per second, etc. That's right. Some channels, gathering some channels more than this bandwidth. Here's data rates needed. For example, for voice, this isn't true. This is wrong. Okay, each of you knows Nyquist rate in sampling theorem. Do you know Nyquist rate? Do you hear me؟ مثل انتصار. احسنتم. Mrs. ابتسام زينب. Yes. Oh, أحسنتم. Mrs. ابتسام. In signal and system, okay? Oh, yes. أحسنتم. Now we straight. In which lecture? Oh, Mrs. Ibrahim. أحسنتم. In which lecture you are familiar with it? With Nike straight? In your undergraduate courses. Ahmed Muhammad. All of you. Mrs. Ibtisam, Mrs. Safa, Mrs. Zainab, Mr. Ahmed Muhammad. In which course are you familiar with it? With Nike straight? Please type. Huh? I said. In which course? In which course? In which lecture? Okay. Did you familiar or did you know familiar with Nike straight? Nike sampling rate. Nike rate for sampling. For sampling. In which course? For example, in Iran. In Iran, we have in electrical engineering in undergraduate a course named Signals and Systems. Okay. Its reference book is by written Signal and Systems by Mr. Oppenheim. Okay, what was your lecture for your course in undergraduate? Don't type, each of you. Who knows what is Nyquist rate? All of you, what is Nyquist rate? Do you know or not? What is no Nyquist rate? Mrs. Safa, you said yes. I thought you know. Okay. A theorem in sampling. Okay. I say the result of it. Okay. Jahaz means sampling. Its name. What is Jahaz? In Iran we have Jahiziyeh, device. Device course in undergraduate. Maybe. That's right. تقصد جهاز أخذ العينات. I don't know. What do you say, Mr. Naiman? جواز أخذ العينات. Please type in English. Sampling device. Okay. A to D. A to D. In sampling device. Okay, in A to D, sampling rate, frequency or signal. Okay, in DSP lecture, in signal and system lecture, in control lecture, in some hardware lectures, we have A to D, analog to digital converter. Okay, ADC or A to D, A to D or ADC. That's right, analog to digital converter, this device. Okay, A to D. What's the correct sampling rate in A to D? This is the result of Nyquist rate. Nyquist was a scientist. Okay, Nyquist rate, who says the sampling rate must be greater than twice the maximum frequency of the signal. Okay, Nyquist rate or Nyquist theorem. Okay, Nyquist theorem for sampling. He says the rate of sampling in A to Ds or ADCs, okay, must be greater than twice the maximum frequency of the signal. Okay, the input signal, the signal. That's right. Nyquist says the rate of sampling in A to Ds must be greater than twice, multiplied by 2, twice the maximum frequency of the input signal, the analog signal. Okay. Here, for voice in telephony signal, for example. Okay, in telephony voice, for example, or energy of my voice, me as a man and you as a man or a woman, my voice PDF, probability density function of or energy of voice signal is from DC to, for example, 3 kilohertz. Okay, or voice frequency components are in 0 to 3 kilohertz band. Okay, yeah. Or voice men and women, or voice frequency components are in 0, for example, DC to 3 kilohertz band. Okay, thus the sampling rate must be greater than 6 kilohertz, 6 kilo sample per second. Okay, thus the sampling rate must be greater than 2 kilohertz by twice, 6 kilohertz. Okay, greater than. For example, we put some guards from 3 kilohertz to 4 kilohertz. That this is from 0 to 4 kilohertz, and then the sampling rate of 8 kilohertz, 8 kilo sample per second, 8 kilo sample. The better The better one is 8 kilo samples per second. Okay, 8 kilo sample per second. But each sample, kilo samples per second. Okay, KSPS means kilo sample per second, samples per second. But each sample, for example, in standard voice, telephony voice, each sample or A to D is 8 bit A to D. 8 bits A to D. Okay, that means each sample is 8 bits. Thus, or voice digitized stream is 64 kilobit per second. Here, digitized, thus, or digitized voice, standard voice in PCM telephony. Okay, in parentheses, in PCM telephony, in your PCM telephones. Okay, in Iran, in Iraq, in Europe, in America, in PCM telephony is baud rate is 64 kilobit per second. Why 64 kilobit per second? Because 8 kilo sample per second multiplied by 8 bit per sample, not per second, means 64 kilo sample per second. That's right. Ahsant. Okay, this is wrong. Voice is 4 kilobit per second. This is wrong. For voice in standard, in telephony, at least 64 kilobit per second, not 4 kilobit per second. But in hi-fi, you hear it maybe hi-fi. What is hi-fi? Do you know hi-fi in sound? Hi-fi is high fidelity. That is a good quality sound. For example, in concerts, in maybe in dances, etc. Okay, voice of human, voice of some equipments. Okay, jazz, etc. A good quality is recorded. Its name is hi-fi, high fidelity, greater than 64 kilobit per second. In a standard, in voice streams over the web, you see 196 kilobit per second for hi-fi. Okay. أحسنتم. Mrs. ابتسام. Mrs. زينب. أحسنتم. أحسنتم. Okay. For example, this is for music. Okay, a better. Why? Some complex answer. After transferring the data, for example, okay, we must reconstruct the signal. That means we must convert the digitized signal to analog signal. Okay, this is reconstruction. For reconstructing, we need a low pass filter. We put a low pass filter over the digitized signal, and then it's converted from D to A, digital to analog. Okay. A small guard, okay, a small guard, not a wide guard. The reconstruction low pass filter is a sharp, has a sharp shape, okay. A sharp shape in filter amplitude results in a disturbances in phase of the signal, okay. For example, we say it jitter, some noise in signal, and or air is some mistakes, okay. Is a complex answer. I think the time for the lecture. Oh, Mr. Intasar. Oh, you said okay. Okay, right. You have a class after it. You have a class or not? You have a class with Dr. Shakur or not? Some of you? Okay. That's right. That's right. There's another question? Yes. Hello. No. There isn't any question? No. مخلص. أنا تايب في أمان الله. Okay. Oh, Miss Muhammad. مخلصين العودين. Okay. I put the link of recorded file over the LMS and this file beside the Telegram over the LMS. Okay, this PDF file. To tomorrow. See you later for tomorrow, inshallah. Let's stop recording and end of meeting. في أمان الله وحفظه. أحسنت. شكرا. بس انتصار. Mrs. نعيمة. Mrs. Hannah. في أمان الله. Mrs. Safa. All of you.